Okay, so the focus today is going to be futures as an exemplar monad. We're going to be discussing monads more generally within a coming lecture. We've already seen a number of monads within this class: option, try, stream, and several others that we've referred to glancingly. Futures are another interesting one. Monads are these containers that contain objects that supplement values within them with additional data, metadata. For example, is a value even here or not? So the option monad, it could contain a value or contain nothing. Futures are a similar type of construct. As a monadic construct, they maintain values, but they maintain it with extra metadata. Has it been computed yet? And a future is something that you can view as a promise of a value. The value may be in hand already, or it may be something that's still being computed, and when it's good and ready, it will be available and computation will continue. Okay. Now, much of the impetus for monads goes back to some of the things we talked about just half an hour ago, or over the past half hour. The fact that writing concurrent code is challenging. It's challenging in large part, because of dependencies. A can depend on B. And when we have dependencies, from a computational standpoint, it brings up lots of challenges. We have to make sure that if A depends on B, that B is ready to produce that value before A can use it. And there's synchronization issues. There's issues having to do with making sure the fact we're not looking at that value, A depends on B, at that value being produced by B when it's still in the process of being changed, when it's still in the process of being put together. We have to make sure that we only look at that value when it's good and ready. It's actually fully ready, not that it's being modified out. When we have two separate threads of computation, whether they're going on truly in parallel or sort of switched between them, we want to make sure that they synchronize properly, in the sense that we're not in the middle of doing something with one when the other looks at it or changes it out from under it. In an asynchronous computation, particularly, we're dealing with a mode of operation for performing things concurrently where we basically request that something happens, and rather than blocking until it completes, we are going to let that go off, do its thing while we continue on our work, and when that value is ready, we will be notified about it at some level. What's one way of notifying things? Think about those who are in 332. What's one way of getting notified when something's ready? Maybe you're plugging in a device and the work starts, and you want to be notified when that device is good and ready. What do you put in place? In a language like C, what's the way you do this? You put in place a what? It has a C, it starts with a C. Sorry? You could do it with a closure. Closure is a beautiful way to do it. I like you think about closures. It has a B in it. Callback. Yeah, you have a callback, right? You have something which you basically say, hey, do this, and call me back when you're done. And then I'll act on it, right? That's a traditional way of dealing with asynchronous computation. Go off and do this, and when you're done with it, let me know. You have this callback. You pass it a function, pointer to a function, say in C, that gets called when it's done, right? And in general, there's a lot of cases where we need these sort of operations. We go to read a web page, and rather than waiting for the site to be contacted and read and the value to be obtained and only then going on, we'd like to be able to continue our operations and just, when that value is available, use it. It turns out that futures provide a way of handling this asynchronicity in a very clean, scalable, easy to reason about fashion. And the way they do this is they represent future values, promises of values. And the point is, we can handle them right now. We can operate on them right now. We can do things with them right now. Go on, describe the full computation, and when that value happens to be available, all those things will take place. We can go on and delineate what this computation is, how it will take place, and whenever that value is needed, it can block for it, if desired. But when it becomes available, all these things will end up happening. And this is going to capture in one place, in contrast to callbacks, where the code is often distributed between that function that you pass it and pass off to the to this thing to say, call this function back, and this other code. Rather than having all that logic distributed many places, here the logic is clear. It's laid out in a way that often has a clear pipeline associated with it. So, suppose here that we want to wait for user input for a search term, right? Or we want to perform a search with that search term. We want to harvest content from URLs that result from this search. We want to then perform some sort of intensive computation, which could take seconds to complete on the results, and then we want to summarize it. A lot of these are operations that can take a long time. And if we want to have a responsive user interface, we don't want to just be blocking for these operations, blocking for the user input. We'd like to be able to make sure our system is responsive in other ways. Performing the search, using a search term, that can take some time. We don't want to block operations along these ways. So here we're going to have a set of operations that can take some time, and that can end up requiring extra complexity if we just block it. So what I'm going to do now is we're going to go use the Scala shell to explore futures a little bit, and I'm going to ask you to go and import a couple of items so that we can undertake these operations in as simple a way as possible. So I'd like you to call up your Scala shell if you could, and I'll direct you to do a couple imports here just so that you can easily follow along with the example. So we're going to go, and we're going to go over here, okay? And what I'll do is I will ask you to go. We're going to import some items that are going to give us access to the futures themselves, and we're going to get access to items that are that will provide us a really easy way of getting data. So I'd like you to import scala.io.underbar. This is going to provide us with a way of reading in from URLs very easily here. And I'd like you to get this scala.concurrent.execution context.implicits.global. That's a bit of a mouthful. Let me read that out to you. It's scala.concurrent.execution context with capital E and capital C dot implicits with capital I dot global. Okay. Okay. So this is going to be very useful for certain types of command line processing with the future. Okay. And finally, and arguably most importantly, I'd like you to import here Scala.concurrent.future. Okay. Those are going to be our main ones that we're going to be using. Okay. So a future here is going to be a promise. Sorry, there's some swapping going on right here. A future is going to be a promise of a future value. And the way in which we're going to produce this is by using the following type of syntax. So I'm going to create a future value here, and I'm going to do capital, oh my gosh, okay, future, and in this little bit of code, putting the, oh gosh, let's see it. So let me go and probe the size here. There we go. You're going to put in curly brackets here some code. So this is, like all things in Scala, this is going to be an expression. Or most things, I should say. This is going to be an expression. The fact that we put it in curlies just allows us to have multiple successive things within it, separated by semicolons easily. So we're going to put in here the simplest case, where it's just a number, right? 3. So here we're going to get a future that is the most trivial type, just a value directly. Now, you'll notice that when I get this future, it's type parameterized, so it's a future int, right? And you'll see something here that you recognize. What does that look like? Yeah, it's a try. It's a successful try. It's a successful try. And indeed, what we're going to see is that try is central to the use of futures. Let's put something else in there that's a bad thing. Kind of makes you wonder, what if there's an error here, right?
So 3 equals 2 or something.
What's that?
3 equals 2?
Well, how if we had something like this, right? Okay, so you might think this is gonna be a useful thing, but what you're actually going to see is that my future one is just here in an empty list. This is something which is not in fact immediately present. And then you're going to see when it actually computes it. This empty list is basically, it's a promise. It's not yet ready. And here, once it computes, it's what happened. It's a divide by 0 error. So it's a failure. What sort of thing is this? This is a try as well, right? Okay, I'll try to pull that up. I notice people are having trouble seeing it. And again, I apologize. We'll have to probe that. Do you see this?
Yeah.
Yeah, it's a failure. You should see that in your own code, right? So here we have something which actually wasn't immediately available, and we'll see how we can find that information out. And then we see something that is available, but it indicates a failure. It indicates a promise which didn't work out. It tried it, but it didn't work out. Now this future one, it has lots of operations that can be performed for it. One of them, which is quite new, is completed. So we're going to use that one here. Future one dot is completed, and here it says, okay, it's complete. It has a promise. It fully acted on that promise, and it received back either a success or failure. But it acted on the promise. It's completed. The promise was delivered in the sense that it went through with it. In some cases, it may yield success. In some cases, it may yield a failure, right? So here, if we go back to this case, this too will yield my future 2 here will yield a case where it is now complete. Okay, these are the most trivial thing, something that succeeds, something that fails directly. Let's try something that's a little bit more interesting. Okay, what I'm going to put in place here would be something where we are going to say thread dot sleep, okay, and we're going to sleep for some amount of time. I'm going to make it 30,000 milliseconds. In other words, 30 seconds. And after that, we're going to have a value returned, 5. Okay, maybe I'll call this my future 3 here. Okay, there we go. So my future 3 is a promise. Is it completed yet? No. You'll notice that because it's not completed, it still is in this type of situation. And over time, here we go, after 30 seconds, we are going to see that it in fact is going to yield an actual value. Okay, now, in the meantime, we may wish to operate on this. We may wish to, for example, map it. And we'll take whatever value and we'll add 1 to it. Okay, we can do that at any point. So here, if I did that again, here it is. It's not ready yet. You can see it's got a promise that hasn't yet been fully delivered. I can go ahead and map this. I can go ahead and, for example, filter it, right? To see if it's greater than 2. All of these things are themselves futures. My future 4 equals this. Oops, sorry, val my future 4, right? This my future 4 is itself a promise. It's a promise that depends on this earlier promise. My future 4 is not yet completed. Now it is, okay. Finally, it's completed. Whenever that earlier computation completes, my future 4 is going to be able to use it and perform these extra steps on it. So here, we are computing using promises. If the value is available right now, that could take place immediately. If the value is not available, we're constructing this whole computation in terms of the value. So when it becomes available, that computation will take place, right? To make this a little bit more clear here, one of the things we could have done is we could put that in there directly, right? We could have here, I'll start off with a start that will yield a future here, sleep, dot 30,000, let's say, and here we'll have, 3 again, right? This is itself a value. I could say my future 4 dot 4 for each, for example, right? For each of them, maybe I'll print them out, right? Here we go. So this value is not available. I've delineated a computation involving the variable, the value, and finally, when that value is available, this computation takes place. Yes?
So the only information a future holds is what a try holds and if the operation is completed. Right?
Yes. You could think that's a very good summary of that. So it holds critically this extra information. Is the computation complete or not? But other than that, it's basically got to try something that succeeds or fails.
Yeah, like you have no idea what operations have been used on the future.
Correct.
And where it failed other than the error itself.
Yeah. We'll talk about monads that do accumulate that sort of information later. In the frameworks, the Spark framework, which is based around Scala and which makes heavy use of these sort of concepts. In the Spark framework, you're actually accumulating along a complete lineage of where this has come from in the set of operations so that you can throw away the intermediate values and if there's not enough memory, and recompute them later when you need them, rather than keeping them around. That's something where that lineage information is key to reconstructing the values, right? You could toss them because you know how to get them back if you need them. And that's an example of a monad, which is keeping additional metadata. But in this case, it's very simple metadata. It's, is it computed or not yet? Now, this my future 4, I need to make this much smaller so you can see here. But my future 4 up there, that was something where I actually had this long operation after that. So I had a sleep, but then I also mapped it with this, and I filtered it with that. And that my future 4 value was one that's just a promise right now. But it's a promise I could say, hey, when it's available, do this thing with it. So this is a computation involving a promise as well, right? It's a promise that hasn't yet been delivered on. How do I know it hasn't yet been delivered on this? How do I know that this value, my future 4, is not yet available? Nothing's been printed yet. But in the fullness of time, when it is available, and it'll probably be a few seconds more, there's my value, right? The promise has been delivered on now. The value got delivered, so it was able to then perform this operation. So here, ladies and gentlemen, it's like we're constructing whole sets of computations around promissory notes, these notes about what will be available in the future. We can fully delineate those computations. We can manipulate these things as if they are values, with the assurance that if there's a value that where at some point it needs this information, it can appropriately block for it. And let's see how that's done. So let's go back and we'll take a look at these slides. So we've been fooling around with use of futures. Here we are having a use of ids completed that will basically test whether or not the value is used. And we've been performing maps with it and filters with it. There is an option of flat mapping it, where flat map, we just like map with the exception of the fact that this function we pass in, rather than just being something that returns any old value, which actually itself returns a future, right? So, for example, flat map, we might take this value we've gotten, this value that when it's available, from a user's input, for example. We've been waiting for this user's input, so we just have a future int. It's going to depend on the user entering it. It's a future int at this point. We perform if we want to perform a map on it, we could take that future int and add 1 to it. With a flat map, we could take that future int and use it to go, for example, look up information for that day from maybe it's a day number, from a website for what was the weather on that day. So here we get back a future of a string that was, a description of the weather on that day, right? So here, given an int, we'd get a promissory note to a string, where that string would itself require some time to compute, potentially. Okay, so these are monads. We could perform flat map on them, and we can perform map and filter and indeed reduce, collect, etc. Let's look at some other things that we can do with them, though. One thing we could do is we could ask for its value. So we'll go back to our Scala shell here, and we will go and ask for the value. Now, here we go. We'll ask for this. This is value, and there we are. There we have its value. Okay. Notice that this is an option. Why an option? Yeah.
The question about futures and user input.
Yeah.
If you ask for a future of somebody typing something in, what does the REPL do? Because it can't move on because it needs to ask you for the data, but it can't ask you for the data because it needs to move on.
Let's go see. Right. we've done some similar things in the past. We've, for example, done a read int, right? For example, and here we can get back a value, right? So let's try this. So we will put something like this, right? Value my future 5. Okay, here we go. Okay, so here it's seeking some user input from the command line, and we haven't provided it, right? Why haven't we provided it? Well, because it's gone on and already asking us, okay, what do I do next, right? I'd like to be able to give it this thing, but it's already going on in terms of the Scala shell, right? So this my future 5 here is going to. Okay, that's interesting. I was thinking it was just going to be perpetually waiting for this thing because it wasn't actually going to be able to get this. So this suggests that it actually attempted to read something and got back a value for it. So let's try this, my future 5. Okay. So here it is. So it looks like what actually is going on, yes, is that in terms of the interaction between it and the Scala shell, it actually is waiting on the input there and receiving the next thing I type as the input for the read int here.
And if it's not, Scala will also interpret what the next thing you type as commands.
I'm not sure about that. Let's try that. So I'm going to say foo here. Okay. All I found was so I'll do again. I'll say foo. What it's doing is, I think basically it's taking as many characters. Okay, so this is really interesting. There's no, it's not timing out. I think there's some sort of subtle interaction that I'm not picking up between its input and what the Scala shell is inputting, because essentially when I type some things, it's able to, yeah. Okay, okay. This is. I'm not sure it's worth pursuing this, but there's some sort of interaction between its input and the input for the Scala shell. So I'm going to say 23 here, and let's see what it got as my future 5 here. Did it get the full 23? No, it just got the 2. Okay.
So it really doesn't work in terms of the REPL. It doesn't work the way you need it.
Well, in terms of the REPL, the user input idea doesn't. But if this were for example, if this happened to be a type of input that didn't depend on the REPL, like a message box or something like that, an edit box where I could enter things, it should work fine. I mean, the general principle isn't affected by it. It's just that what is affecting it is in the REPL, it's the read val print loop here. It's somehow trying to multiplex this input, and some of it is going to this read int, and some of it is going to the Scala shell, and there's probably some logic to it that I don't fully grok.
At least on mine, it seems to take every second character, which I'm not sure if there's any logical reasoning beyond that.
Okay, that's interesting. So let's that's fantastic. So I'm going to try this. I'll try 1, 2, 3, and probably it will be getting 4, 5. Okay, so it should get 1, 3, 5. Here we go. My future 5. Mumble. Okay. Okay. Moving right along.
So it's just random. Is that did we just create a race condition on read?
Well, that's what I'm wondering. I mean, there's some curious things here, and but this is kind of an artifact of the fact that the REPL is also depending on the user input together with this readout, so it doesn't make for a nice example.
I'm guessing they both attach to the right buffer, and just whoever pulls it out first gets it.
Possibly, yeah, and eliminates it from the next one getting it. Okay, so here we are we were seeking though to check out value here, and what we can see is that my future 5 can be rendered as a value here, in which case we'll get an option. Why an option? Why an option? Why not something? So this is an option of a try event. Why isn't it always try event? Why isn't this always a try event? Well, let's go back to this earlier long computation. Okay, here we go. My future 6. Here we go. Here's this long computation. If I say my future 6 dot value, what will I see right now? None. It'll be none. At what point will that change? Yeah, when it's completed, right? At that point, there's going to be a value available. And so this option basically encodes, in terms of value here, whether or not it's been completed yet. If it's none, it hasn't acted on the promise yet. It hasn't fully acted on the promise, fully tried the promise. But when the value is completed, it's at that point that we'll have a sum here, right?
So if it was just try, you would only have the options for
Success and failure, which neither of which apply if it hasn't been fully tried yet. Yeah, that's right. So this provides us a way of characterizing those successive possibilities. Beyond that, and the sort of standard operations like collect that are reflective of sort of standard processing associated with monads, we have a couple more things here. One is that we have onComplete. So here, basically, we can take the result of the promise, try, when it is available. So when it is completed, we can do something that will go and take that value and operate on it. Now, this is something which can then, for example, perform some side effect like put it in a database or what have you. OnSuccess would operate specifically for the context where it's successful and otherwise not operate. We can also block for the result using results, and here we have a certain amount of time that we can give that we're willing to block, and if that time is exceeded, then we can end up in a situation where we'll time out. A timeout and cause a thrown exception. Okay, so I believe the syntax there, I've got to double check the syntax, but it needs a duration here. So if I'm going to go create another one of these things, I'll create a future, and this future will again sleep for 30 seconds here. And if I say here that I want to perform this result, this is going to block. And I believe the syntax that one would use here would be something along this. And I've got to check my recollection of this. Nope, it's not. Is it 30 dots? Okay. Unfortunately, my recollection of this is incomplete. Yes, it needs a duration. So import Scala.concurrent.duration. Okay, and I'm going to import everything from there, and in fact everything from this. And I thought there was a way to do this. Okay. Okay. Yeah. So let's see. 30 millis. Okay. Unfortunately, I'm having trouble encoding this as a duration. Let's just see. Is there a? Okay. Yeah. No. I'll have to go figure out the syntax for that. In any case, I could go here and do a result, and I would have a timeout duration, and it would throw an exception if it didn't get it within a certain amount of time. Transform here basically provides a way of handling either success or failure with two different operations, and then similar to on success, there's an on failure operation, which is going to handle it for the case where there's a failure that's occurred. If there's a failure, in that case, it will perform a function to clean up the results. So we can have on success, on failure, each of which handle one particular case, or we can have transform, which provides two functions, one to handle success and one to handle failure here. Okay, so these futures are ways of computing with promissory notes, and when that value is available, they'll allow us to go act on it. Okay? A couple more things about them. Here, if we have a note such as this, because we can perform computations with it, we can construct larger pipelines. This is actually somewhat of a fun example, so we'll spend just a moment on this. So I asked you to import here the Scala.io package, and we're going to make use of that. We may also need this Scala.util, so I'm going to import that here. Import Scala.util. There we go. And we're going to here read from a URL, and we will then make it into a string. So here, val my future 8 here. So we'll do a future. And here we are going to do source dot from URL, and we will read a URL here associated with usask, and we will make string. So this is a future of a string. Initially, it's not available because it hasn't yet accessed the contents, but in the fullness of time, okay, unknown host.
HTTP.
Okay. No, it's actually because I'm not on the net here. Okay. Okay. On yours, presumably, if you're connected with the network, yours yields a value. Does it yield a value? Yeah. Try it with HTTPS as well. Try that with HTTPS. I think both of them will actually yield value successfully, right? So this again is an operation. This from URL, which can take a while. It can take a while because of a timeout. It can take a while because it just requires time to go over, parse the web page, get the value back. And here again, we're computing with a future value. But this value is something where just because it's not available, doesn't mean we can't do something with it. We in fact can delineate, a large pipeline that we want to perform with it. Where here we split it up, and basically we are grouping words according to whether one, the count of the count of words of certain sorts. So we take a word and we basically count how many instances of that word there are on the page, and we sort them appropriately. Okay. So you could imagine, for example, going and getting a submitted search term. This is a future of a string as submitted by a user, presumably not with the REPL. We go and we perform a web search using that item, using flat map. Why is this flat map instead of map? Why are we flat mapping this to perform a web search?
So you get the URLs, not the URLs?
Not the what URL?
The future or the option URLs?
Yeah, yeah. Well, both flat map and map would be operating on the value within the monad, within the future. So in both cases, they'd be getting the string that represents the URL that's returned from this guy here. So flat map and map both operate in terms of, you know, what's inside the monad. In this case, it's a string. How do they differ? Flat map does what?
It returns it as a string.
Yeah, the function flat map takes in itself returns a future, not simply a value. So map, the function that I pass in takes a value, a string, and it returns a value. Flat map, it takes a value and it returns a future. Returns a future. That's the difference between flat map and map. Just like remember when we first used flat map, we were operating on a list, for example, or an array of strings that were words, and we wanted to, or that were, sorry, lines within a thesis, lines in a document, and we performed a flat map that took a line and it returned itself an array of words. Remember that? And we wanted to perform a flat map rather than a map, because if we'd done map, we would have gotten a nested array, an array of arrays. But here we wanted to get a single array out of it. So it is here with flat map. We have a future of a string. If we had done map of a function that returned a future, we would have had a future of a future, right? We instead want to do a flat map, because here we have an operation itself that will return a future, and we want to get out a future from that. So that gives us a future, ladies and gentlemen, of some URL back from this web search, that flat map. And then we'll map that future URL to go and, in fact, we'll extract the links actually. So that gives back a URL. We need to actually then get the string from that URL and then map that to extract the links. Oh, excuse me. Yeah, there's something broken here. We want to extract links here, and then we want to basically go and, okay, so I was thinking that's a future of a list of a URL, okay. We want to, there's a missing thing here to extract the text, then extract the links from the text, and all of these are operating in terms of futures so far. And then we will eventually get out a stream of URLs here, and then that will give us back a stream of futures of strings by reading the URL contents, and then we are going to perform a long-standing operation on it that will give us a stream of futures of doubles, and then we will add the doubles up in a certain way. So here we're operating in terms of a series of operations, many of which themselves require time to apply successive steps. And because of that, we are performing operations in a way that use methods like flat map, which take in, so when you call flat map, it takes in a function that takes the value that's within the future when it is available, and itself returns a future. Because the thing we're performing takes time. And so this function within the flat map is something that itself returns a promissory note to some work to be done. So that's why we're calling flat map rather than map here, because it requires time to perform this web search. It requires time to perform that operation. Okay? So I want to emphasize here, flat map and map are different. Map is something which takes in a value, returns a value. flat map is something that takes in a value. Flat map is something, not speaking well. Flat map is something that takes a function that takes in a value. Map is something that takes a function that takes in a value and returns a value. Flat map is something that takes a function whose job in life is to take in a value and return a monad, a future, in this case. So here we have a computation performed with a computable future that itself contains stages which themselves take time, and therefore they return promissory notes. They return futures. Okay. Computable futures make it quite easy to perform this kind of asynchronous computation by allowing us to operate on values as if we have them in hand, when really they are just promises of values. And it lets us delineate large computations which can operate in terms of the values, so that when those values are available, they're automatically processed. In contrast to a situation where we're passing around callbacks. With callbacks, we have a situation where the computation is distributed. It's distributed among many places. It's distributed between the thing that gives off the callback and the thing and the code that's actually in the callback to process the value. In our case, we can have successive operations clearly delineated within the context of our code, something like this with stages of computation, and those successive stages put all in one place in a clearer fashion what needs to happen with that value in a way that allows it to be quite transparent. Rather than having the computation divided up between several places, that computation can be just in the standard flow of the program, because we're operating on promissory values rather than on rather than passing around things that force us to explicitly think about when this is available, do that. Okay, so that's all for today, and I will go and go figure out the syntax for durations and get that in there.